Planck's groundbreaking work in 1900 was received with skepticism initially. Of course, most scientists thought the agreement of the Planck distribution was a curious agreement, but felt there could still be an explanation using the rules of classical physics. And there was still no evidence for a light particle called a photon. However, Einstein used Planck's work to explain another unexplained observation in 1905, the photoelectric effect. Recall, the atom is made of protons and neutrons in the nucleus. The electrons are outside the nucleus. These electrons are bound to the nucleus by some attraction energy or binding energy. This energy must be overcome to break the attraction and eject the electron. When the electron is ejected by light, or a photon, we call this the photoelectric effect. Again, in 1905, there was only a hypothesis that light can be a particle, but no evidence. Here is the experiment as we know it today. Imagine a metal surface of atoms. These atoms have valence electrons, shown here in blue. Energy can be introduced by photons. The photon energy is h nu, where nu is the frequency and h is Planck's constant. The frequency required to break the electron's attraction to the nucleus is called the frequency threshold, and usually denoted with a naught symbol. Notice the same symbol is used for the energy to denote the energy threshold. This is called the work function. The work function is also denoted by the letter phi. Einstein's explanation of the photoelectric effect seems simple now, but was somewhat radical at the time. Clearly, energy is proportional to the frequency. So if low frequency, low energy photons hit the surface of the metal, no electrons are ejected. There isn't enough energy to break the binding energy requirement. And no electrons are ejected regardless of intensity. More on intensity in a moment. Now, if high frequency, high energy photons hit the metal surface, there is enough energy to break the binding energy and electrons are ejected. The electrons then hit a detector where we can measure their kinetic energies based on the current produced from the moving electron charge. Let's look at the math, which is surprisingly very simple, to make the connection to quantum mechanics. A photon of some energy strikes the metal surface. If enough energy is present, some of that energy goes into breaking the binding energy, so we subtract the work function. Due to the laws of conservation, the electron carries this energy with it as it moves. This is the kinetic energy of the electron. Indeed, experimental data of the electron's energy in terms of electron volts versus the frequency of radiation shows a linear plot as the equation suggests. But here's a major significance. The electron energy is independent of the light intensity and only dependent on the frequency. Let's look at wave intensity for a moment. Wave intensity is referring to the amplitude of the wave. Here's a funny picture I found online. One bird's sound has some frequency, while the other bird's sound has the same frequency but more amplitude or intensity. A similar comparison can be made for electromagnetic radiation or light waves. Here are the major conclusions of the photoelectric effect. According to classical mechanics, electrons should be ejected at any frequency of light, so long as the intensity is sufficiently high. But that's not what we observe experimentally. What we observe is that the electrons are only ejected by light with the threshold frequency and independent of the intensity. Furthermore, recall, Planck predicts the energy of the photon to be h nu, which I'll substitute in this equation. According to the experiment, the slope of the line is equal to Planck's constant. Let this result sink in for just a moment. In two seemingly unrelated experiments, Planck's constant appears in both Planck's distribution and in the photoelectric effect. This makes Planck's constant a universal constant. But this is even more extraordinary, certainly in 1905. According to classical mechanics, the light wave meeting the threshold energy should distribute itself over the surface of the metal. But if this were true, then the dispersed energy would not be enough to eject the electron. Instead, the light wave should impart all its energy to that single electron, like two particles hitting each other. This means that the light wave should also behave as a particle, thus appearing to introduce the wave-particle duality. Fun fact: did you know Einstein won his Nobel Prize in 1921 for his work not in relativity, but for his work on the photoelectric effect?